I will be very quick, sure. I think I will just do that and then I will just let Bill go.
The broadcast is now starting. All attendees are in listen-only mode.
Good afternoon, everybody from Colorado Mountain Time. I am not in Mountain Time right now, but this this thing, our company, I think is always based in Colorado, so I always go with the Mountain Time. So this is a read this time. Hello, everyone, and we have Bill with us. So say hi, Bill, to everyone.
Hello.
Yeah. So we had this webinar like the last time also, but because of some technical issues, we kind of was not able to attend his presentation. So it is a sheer pleasure to have him on again, and I think it says just I think it's really sweet of him to be on with us again. So today's webinar is all about his presentation. We already have the interview session with us, which is already recorded and is on our website available if you want to go in. And this time we go the live presentation. We'll attend that, and then this will be also available on our website. So throw in some ones if you can hear me, and if there is some technical difficulties or you cannot hear us, just like try to put twos or for any reason technical issues. Mm.
I'd be happy to do that. Do I need to close this screen that has a picture of me on it?
Um, can you see your presentation clearly?
Yeah, the one that says,
Yeah, you can just move it. Yeah, minimize it.
let's see, how do I do that? Yeah, I could drag it, but I'll just put it off to the side. Well, first of all, thank you again for inviting me back. I sincerely appreciate it. For those of you I have not yet met, my name is Bill Cobb. I'm a retired communications executive, and I've been fortunate to be part of the evolution of that industry for a lifetime. And unless you've been sleeping under a rock someplace, you probably noticed that the communications industry has changed dramatically since its beginning. And since it basically has been shaped by research, innovation, and collaboration, I thought those traits might be interesting to share with you because of what it is you're trying to accomplish. What you're working on is going to take research, innovation, and collaboration to accomplish. So if you'll bear with me for the next half hour or so, I will take you on a journey that has changed the world. Our journey starts about I would say it's more than one century ago. It started in the late 1800s, and it began with Alexander Graham Bell making a telephone call to his laboratory assistant. And that phone call found a way to take sound waves and convert them into electrical impulses, and then reconvert them back into sound waves at the end of a wire. Now, this was a pretty timely discovery because at that moment in time, the only way people could talk to one another was to write something down in a form of a message or a letter and send it through the postal system. Either that or they had to go down to the railroad depot and send the telex or telegram down to the next railroad depot and hope that somebody would receive it and deliver it. So Alexander Graham Bell patented his invention, which has gone on to be known as the world's most valuable patent. And what he did with that patent is he formed the Bell Telephone Operating Companies. And then shortly thereafter, with the help of his father-in-law, he formed American Telephone and Telegraph, which was AT&T. Now, the original telephone networks were essentially local operations that required an operator who would recognize your phone, ask you who you wanted to talk to, and then would bridge that phone call directly to their line. So in order for that phone call to be completed, there had to be an operator who knew you, knew what line you were calling in on, and who it is you wanted to talk to. Well, this worked well because it could set up a direct connection from person to person, but it didn't scale very well because as more and more people wanted telephones, it required more and more operators and more of these plug-in switchboards. Well, now it would be impossible for the operator to know who you are and know everybody that you might want to talk to. So the whole dynamics of that switchboard operation began to change. People now were identified by numbers, not by name. I would be 1, 2, 3, 4. Ari might be number 6, 7, 8, 9. And the operator would find out who I was and what line I wanted to talk to. Well, sometimes that line would not be on her switchboard. So she would have to hand the call off to another switchboard operator who would then have to go find the person I was going to talk to. And as you would expect, this was not very efficient. So they started breaking it down to see if there might be a better way to do it. Everybody needed a customer device, a phone to talk on. Everybody needed some way to connect to the switching center. Everybody needed to have a switching center to move the calls around. And then there had to be a way to connect the different switching centers. And then, of course, there are all the business issues that go with operating something like that. Well, here's how they began to automate the system. The original system is the one on the left, the simple telephone, the plug operator, and they connected the calls one at a time to one another. Once the rotary dial telephone was invented, they were able to start to mechanize some of that switching requirement. And the one you see there in the middle is what we call an electromechanical switch. And this basically would take the pulsations that came from the telephone, the rotary phone, and move those panels up and down until they got to the places that connected that switch or connected that call. This was used for a number of years, and then finally later on, they were able to replace the electromechanical switching with circuit switching, which is kind of like having an electrical panel, where the impulses from the telephone would trigger the switches that would connect the call. Well, these improvements took time to make. The original telephone operation began in 1878, which was the first manual telephone. But over the years, people invented things and research provided improvements to the system. And you'll notice from some of the names on here that a lot of these peoples were not necessarily Americans. They were from other places around the world. For example, Alexander Keith, John and Charles Erickson, they invented the dial telephone. And then probably one of the most important discoveries was building out the telephone numbering system. And this enabled a way to systematically identify and connect different phone lines, different phone calls. The bell system architecture was built upon what they call a tree. We're down here at the bottom, you and I, we're line code. My phone number is 1234. And I'm connected to an exchange here in Fort Collins, which is identified as 226. So when someone wants to call me, they call 226-1234, and they're connected to my telephone. Well, that's fine if you're calling from the same exchange center. But if you're calling from over here, you can't get to me. The only way you can get to me is by going up to an inter-exchange switch that takes the call from here to here to here, and then back to me. And these inter-exchanges became long-distance exchanges. And here's where area codes were assigned. So to find me, I was at 970-226-1234. And I could talk to anybody else in that 970 area code by just going up there and down to another local exchange. But what happened if I wanted to call cross country, someone in Chicago or New York, I couldn't do that through this exchange. So this exchange would have to call another exchange, which would go look for the local exchange and then look for the phone number that I wanted to talk to. So my phone call had to go from here to here to here to here to here to here. And to do that in a timely manner and not diminish the quality of the call was quite an accomplishment for the Bell system. Now, although the engineers thought this was fabulous, people who were building competitive telephone companies felt that they were locked out of this system because the only way they could connect with somebody who's on the Bell system would be to come in at one of these exchange points and, of course, pay the appropriate fees to do so. Well, all of that worked well for a while, but in 1947, Bell Labs, who was the research arm for the Bell system, discovered the transistor. And the transistor was initially used for amplification to enable longer distance connections to voice calls without diminishing the quality of that. And eventually, as digitization began to take its place in the network, it started to automate switching as well as the amplification process. And this began to increase the capacity of the system and reduce the cost of operating the network. One of the benefits to building the digital framework was that now it was no longer necessary to have a direct point-to-point connection to make a phone call. They found a way to take all of the different variances of the human voice and put it into a packet of 56 kilobits. And what that enabled them to do now is put more than one packet of voice onto a single transmission line. And this meant that now the efficiency of the network had been multiplied. For example, instead of having a point-to-point line that connected 56 kilobits of information, they can now on the same line do almost 30 times as much on that same facility. And then when they added what they now call T3 lines, which were 44 megabits a second, they could do the equivalent of 28 of these 30-time lines. And it became more and more efficient, to say the least. Well, once this was discovered by the innovation world, in 1968, there was a famous decision here in North America, called the Cartophone decision. And Thomas Cartophone had built a cradle device where he would take a telephone, put it in a cradle, and then be able to connect the telephone network to his radio network so that those people could talk to one another. This was being used for things like fire departments, ship-to-shore radio, things of that nature. Well, he petitioned the FCC and said, why can't I connect directly to the Bell telephone system? Why do I have to go through this aberration to make this connection? And the FCC agreed with him. They said, okay, you can connect electronically as long as you don't interfere with how the network operates. Well, once that decision was made, the innovation for the network exploded. The first thing that showed up were electronic key systems, and they would buy one of those wholesale lines, those T1 lines that you could put 30 phone calls on. They would buy one of them and then distribute that capability within their business environment. People realized that since it was a digital connection, they could also move information. And the first attempt at doing that was the introduction of facsimile machines. And then companies that had multiple locations across the country said, why do I need to go through the phone company exchange when I can have my own private business exchange? And therefore, then the only time I have to use the local phone company would be when I need to make a local phone call. And then on top of that, people like NCI and Sprint showed up and said, well, if we can connect local exchanges to private telephones, why can't we connect exchanges to exchanges? And they began interconnecting directly from the long distance switches to those private business environments. So all of this took place as a result of one decision, the Carterphone decision. And what happened after that is what you would expect. Competition began to evolve. Well, while we were worried about protecting the telephone network, out in Silicon Valley, the dot-com boom was starting. Local area networks were pretty prolific at the time, and they were being used in confined environments. For example, business offices or research laboratories, where there would be dumb terminals normally talking to some kind of central processing unit. Well, there were two students, graduate students at Stanford University, who worked in two separate networks. One was working in one research lab, the other was working in another research lab, and they wanted to message one another. Well, there was no way to do it at the time. So they developed a vehicle, a packet switching router, that enabled their networks to talk to one another. And that invention went on to become Cisco Systems. Cisco Systems, the most prominent player in the internet worldwide. Well, that opened the door to create what they call wide area networks. And a wide area network is just a way of connecting all these local networks. For example, at Stanford, all these different laboratory networks together and enable them to talk to one another. Well, since you could do it in an enterprise environment, why couldn't we do it in a public environment and build what we call virtual private networks? Networks that would use the telephone facilities, but would only connect to my servers and my phone systems. And in order for you to use it, you would have to have a password and a domain name that people would on the network would recognize. So all of a sudden, the public switch network, the telephone network, was becoming a data network. And it wasn't because we who ran the telephone company had wanted this to occur. It was because it was going to occur with or without us. Well, we caught on. New networking devices were now required. So if people were going to go out onto our telephone network and use it to transmit their data, we had to have a way to protect the network. So a modem became the essential tool to connect to the internet, where routers that move things around within those local area networks was not necessary to connect to the phone network a modem was. A router provides security measures to protect your network, but a modem candidly does not. So when you took your information, put it out through a modem, out across the public network, there was no way to protect it, not in the early days. Well, people caught on to this concept of being able to use the public network to find information in different places. And next thing that happened, we all know about, is the internet exploded. The internet is a global system of interconnected computer networks. All those local area networks, all those wide area networks can be connected as long as they use the Internet Protocol Suite, which is the language we talk to. It's called TCP/IP, to communicate between the network and the devices that are on there. So any device that gets connected with the universal protocol will have a uniform resource locator address, URL. Sound familiar? Well, a URL is simply www.whatever your website is.com. Well, the reason we have URLs is candidly to make it comfortable for people. So I'm bill.com at outlook.com. That's how you find me. But that's not how the network finds me. The telephone company uses IP addresses, and IP addresses are 32-bit domain names that are, 32-bit numbers that are set up and assigned to our devices. So my computer that I'm talking to you on has its own IP address. So does my printer. So does other elements of my home on my network. So the internet is starting to expand. It is starting to continue to grow. And most importantly, it has driven up the data traffic on the public switch network exponentially. Well, as this event started to occur, the cable companies decided that this might be something that they would like to do. And the cable companies had provided a one-way broadcast network. It was only spitting out movies, information, one way to your home. Well, when they learned about all of this data traffic now transpiring in the telephone network, they decided they were going to enter that arena. And they did so with the cable modem. And here in America, they're very, very popular. And one of the reasons is simply that phone lines can only communicate at 56 kilobits a second. And then if you get a digital phone line, an ISDN line, you can only communicate up to 128 kilobits a second. Well, coaxial cable can do 4,000 kilobits a second. So it dramatically improves the faster speed time you get on and get off of the internet. So a lot of the cable operators, Time Warner, Comcast, began experimenting with telephony. Well, everyone now started complaining about the fact that somebody else was in their business. And the federal government here in America passed what they call the Telecommunications Act of 1996. And basically what the FCC asked for at that time was all of these people that have infrastructure in place that are serving the public need to find a way to provide access to both telecommunication services and advanced services like high-speed internet connection. Well, we all cried foul. Those of us in the telephone business said, we have 100 million miles of wire out there, and we would have to upgrade it all in order to provide high-speed internet connection. The cable companies complain because they say, we're not going to build networks everywhere. We have our own established customer base, and we're going to serve them. We don't have any desire to put in more infrastructure in new places. Well, the federal government here in America, the FCC, said, I've had it with all of you. What we're going to do is going to open up communications to competition. And we're going to do that by releasing electromagnetic spectrum from the military, and we're going to auction it off to anybody who wants to get into the business. Now, if you're an incumbent, you can bid. If you're a new player, you can bid, but the spectrum's got to go to the people who bid for it. So beginning in 1994, the FCC, Federal Communication Commission, here in America, conducted more than 100 different auctions, and they sold that spectrum and raised over $200 billion for the US Treasury. And they say, people spent $200 billion for radio waves, and the answer is, yes, they did. And then they went ahead and spent billions more to start putting up cell towers. Well, what happened is, as the network began to proliferate, somebody came up with a fabulous idea as to how to use it. 2007, the arrival of Apple's smartphone. Now, today, virtually all of us walk around with a smartphone, but you have to recognize how incredibly innovative this invention is. It's a mobile device that combines cellular and mobile computing functions into one single unit. They're distinguished from regular phones because of their stronger hardware capability and the extensive mobile operating systems that enables wider software applications. Now, what does that mean in English? There are currently estimated to be 2,800,000 apps on the iPhone. 2,800,000 apps. Well, where did something like an iPhone come from? I mean, it just showed up. No, it didn't. It's a result from international collaboration. The iPhone comes partly from Germany, partly from Korea, partly from the US, partly from Japan, and probably other places that I don't know about. And it's assembled by a company called Foxconn. Now, Foxconn assembles most of iPhones in Shenzhen, China, but Foxconn is a $5 trillion multinational company that maintains factories in Thailand, Malaysia, Czech Republic, South Korea, Singapore, the Philippines. It is a multinational that has the capacity to integrate all of these elements to meet a specific specification that comes from Apple. Phenomenal. Well, what has this done to the public switch network, the telephone system? Well, as you would expect, traffic has boomed. And it's not telephone traffic anymore, it's data traffic. Right now, we have, in America, have added another 100 cell towers. The subscribers for wireless service has gone up by 100 million people. There are 273 million smartphones that we know of in use in 2017. I don't have later numbers. They were not available for me. I can tell you that the data traffic in the United States has gone from 0.4 of a terabyte to 15.7 terabytes, and it's expected to double by 2023. And if you look at the impact of the smartphone globally, there are 2.5 billion of them in 2014. And now there's 3.1 billion expected to be in use by 2023. Well, what has that done to the data traffic that the telephone companies are going to have to handle? Well, now we're talking in exabytes. And for those of you who don't know what an exabyte is, it's a billion bytes, a billion gigabytes. So you're talking about insane numbers of packets flying around the globe, trying to get to where they need to be as quickly as they can get there. So that's the challenge we've been given in the telecommunications industry. Well, what happens next? Well, if you've been noticing, the wireless network access speeds have been improving. We've gone from 1G, which was about 2.5 kilobits a second, to where most of the networks are today, 4G, which is about 100 megabits a second. But 5G, which is now being deployed and agreed to by 19 companies around the globe, 19, is going to enable 1 gigabit of transmission from your phone to some cell tower. 1 gigabit. Now just think about how much information you can move, what kind of imaging you can move, what kind of real-time devices can be utilized with that kind of bandwidth. Who knows? We'll find out. So if all of that traffic is coming onto the network, what do we do with it? How do we move it around? Well, in telecommunications, packet switching is the method of grouping all of that data and putting it into what we call packets, little bundles that have a name and a payload. The name, the header, says, I need to go to see a reader. Okay, so what happens to that piece of data? It goes into the network to one of these routers. And the router has to read that header and say, okay, you want me to send you where? And then it has to determine the best way to get it there. Now, there's one big difference in this environment versus the one we started with. It no longer takes a direct connection to complete the journey. Remember, in the circuit switch, the old tree architecture, we had to set up a direct link between point A and point B to complete a call. Well, here, in order for that digitized call to get from here to here, it can go a number of different ways. And if it happens to be information, it can take the same route. So what we have now is a new switching environment. Well, in order for this to work, this mesh architecture, they have to be pretty smart routers, right? Yes, they do. And excuse me, here's the way they operate. Your call comes into one of these routing locations. They read the header. They say, I need to take this information to here. Well, they have to also determine what's the best route to get it there. So they have to process an incredible number of instructions and then execute those instructions in order to get that information to go where it needs to be. Well, how do they do that? Well, if you've been following a little bit of the data processing world, you'll discover that processors now are incredibly smart. Back in 1995, when Intel first came into the marketplace, the Intel Premium processor could handle about 541 million instructions per second, and then process 200 million instructions per second once it determined what it needed to do. But Intel continued to develop, and the iCore i7 does 147,000 million instructions a second and can process 3.3 billion instructions that can execute those within a second. Well, Intel has now come out with a new processor, the i9 in 2021. And while I don't have all the details on it, but it can execute the instructions that it's given at 5 billion times in a second. Now think about how phenomenal that is. But you say, well, do we really need that? The answer is yes. Now, how do you get the traffic from here to here and here to here if all of these processors and all of these routers are sending this information out over these pipes? They have to be pretty big pipes in order to accommodate all of that traffic. Well, those pipes are no longer electronic. They're now optical. And that traffic is not represented with electrical impulses anymore. It's recommended with photons. And what optical transmission has done, it has multiplied the utility of those transmission links. And if you look at that, how that has evolved over the last several years, you'll see that it went from being able to move 61 million bits per second to 622 million to 2 billion bits to 9 billion bits. And now on the drawing boards, they're talking about 39,813 million bits within a second. So all of that traffic that's coming out of these routers is now going over these optical links to get to the router that can send it to its final destination. So what does all of this mean? Well, it means that the new ubiquitous public network is a network that will enable almost everything. We call it a mesh network, a device mesh network architecture. And what the architecture is designed to do is enable machine-to-machine communication. Because there are so many mobile devices out there that need to talk to other devices somewhere else. And the only way they can do that is over a broadband digital network that has the capacity to handle that kind of volume. So let's just regroup here a second and look at what happened. The wired line network architecture that supported voice traffic for all of those years was not robust enough to handle the new requirements of this device mesh architecture. In our country, our government decided to open up wireless spectrum to enable that connection to be made economically and also at bandwidths that could support the architecture. Those cell towers are now connected to switching centers that handle the new kind of traffic, packet switching and routers. Every one of these switching centers now has a rack of routers which turns around, processes those signals, and determines where it needs to go. Most of those switching centers now are connected to other switching centers by fiber optics, which are very robust and can handle incredible amounts of bandwidth simultaneously. Now, the thing that really makes this interesting is how quickly this happens and how transparently it happens. The speed of light is 186,000 miles per second. So one of these connections can literally go around the world almost 7 times in a second. So for those of us who are human beings, we connect to anywhere in the world, and it appears to be instantaneous. Well, it is almost instantaneous. It's seconds. Seconds, that's all it is. So where do we go from here? Well, communication never sleeps. The industry has evolved for more than 100 years and will probably push the envelope wherever it is possible to do so. I don't know if you've been paying attention, but we have just made our first interplanetary telephone call. Percy. Percy is on Mars and Percy is talking to Earth and back and forth. So who knows what's next, right? But whatever the future holds, I believe communications companies will provide the connectivity and the routing that will enable that to happen. And the future is enabled by communications. And I think the lesson from this presentation for you should be simply that. It all seemed impossible 20 years ago, 25 years ago. And look where it is now. I don't think there's a person on this seminar who doesn't have a smartphone and doesn't use it. I'm at a stage of life where I have grandchildren, and I assure you they know how to access information anywhere in the world by pushing buttons, and it's wonderful to see. So with that, I'm going to challenge all of you to do what you do best. Find the solutions to the problem you're working on. Do what you can to make the world a better place, because the one you're working on is equally important, if not more important. And it's going to take research, innovation, and collaboration. So thank you for listening.
It was a beautiful business. Yeah. We have a few questions. Yeah. I think I will look at those, Mark. So I think first one, I think because we are sustainability platform here. So the question is, what is the role of those radioactive rays coming out of these towers? We are trying to make world more technological. We are in that game now. But what about those effects, like which comes from these radiation frequencies or these rays? Is it sustainable? Like if we try to grow these communication towers or and these the rapid speed it's going on with. So what do you think? Is there any solution or sustainability point of view in these, which like from these rays basically, because they are harmful. Everyone knows.
Well, I think it's a question of degrees, and I don't have an answer for you. I can tell you this, that the industry has an organization called the Cellular Telecommunications Industry Association, and they work with the medical profession to try and measure the impact of all that electromagnetic spectrum that's in play and being used. So far, there's been nothing definitive recorded or defined. I know that there were similar concerns around electric power lines at one time, and they throw off a heck of a lot more than the cellular towers do. But I don't have an answer for that question. I can only tell you that I know people are addressing it and looking at it, and probably take some research to define the limitations.
Okay. And the second question is like, I think they're talking about the security threat and privacy threat because of the advanced boom. And earlier, the security threat was not, privacy threat was not there, but now big corporations like Facebook and Google, they are being accused of data theft and trying to manipulate the results of such things. So is there any association which is concerned about this theft when we are going towards advancement? But what about the communication theft?
Well, here's the challenge for the communications industry. We're required by law to be ubiquitous, meaning that we provide an infrastructure that anyone can use. Facebook, TikTok, all of those, Twitter, they are basically virtual private networks. They are networks that ride on top of our network. And our network, as I showed you with the way they package the packets, we control the header, we do not control the payload. So whatever you put on your bits and bytes Our job is to deliver it to where it needs to go, but we do not scrutinize what is on that payload. That is outside of our purview. We are an enabler. We are not a content provider.
Uh,
Now, I know companies like, to your point, like Fakeless are trying to emulate that role, but that's not their role. They are not enablers. We're the enabler. They are a private network that does something different because they're managing content. We are not managing content.
Smart. Good answer. Yeah. Yeah. I think, yeah.
Well, I think, we're in a gray area, at least in our country, because of our Constitution. But I think the original intent of companies like Facebook and Twitter and TikTok were originally to enable people to socialize with one another. They were not originally intended to be a platform for other people to use for other purposes. And where they got into that gray area, and this is the debate between Apple and Facebook right now, is they started selling information about their users. That's Facebook's business model. So obviously, the more users they can put on the network, the more information they can garner and the more valuable that information becomes. So they've allowed things like advertising on their network. They've allowed platforms to develop that are networks on top of their network that promote different political points of views or economic point of views. And since it resides on Facebook or Twitter's private virtual network, it's not something we get involved with, but I think it's something that probably will require some oversight somewhere down the road so that it's not misused for the wrong purposes.
Perfect.
Remember, our industry we have oversight. We have the Federal Communications Commission here in America, and there are comparable commissions like that around the globe to make sure that we remain ubiquitous and affordable and available to as many people as we can make it. Again, how they use it, we have no control over that.
Good answer. Okay, next one is sustainability concerning the future in a way that what do you think, how long it will take to use this technology and these communication devices to colonize a different planet?
Well, let me tell you what I think is encouraging. We have the same problem, but not to the degree some of the developing nations have. But rural America does not have access to a lot of technology. And one of the things the industry is trying to come up with now is we call them mini cells. Instead of having to build a cell site that has to have the same economic considerations before it's put in place, we're looking at maybe providing mini cells on a public-private partnership so that the community can get what it needs and we don't have to go broke providing it for them. So those kind of things are being explored because everyone benefits from interconnectivity. And here in America, a lot of our rural communities are big agricultural centers, and the connectivity would be beneficial for them. So, yeah, how are we going to solve the problem? As I indicated earlier, there are 19 countries right now who've agreed to deploy the next level throughout their system. And then, the question is, how many more countries can we engage to do similar things? Because I believe electricity and communications are the cornerstones for economic development.
Yeah. Good answer. Well, Mark, can you see if you have any more questions there?
No, I think that's a good question. I'm obviously at the later stages of my career, so I'm not out there running around. But I am on LinkedIn, which I think is a good professional organization, and I can be messaged there. And I do provide this particular presentation often to our local municipalities, our local communities, who are working on trying to solve the broadband access problem. So you can learn about me on LinkedIn. You can learn about what I'm up to. I also have a little blog going on where I'm sharing experience and lessons learned from different activities that I've been involved in over the years. And we take questions. So LinkedIn is probably the best way to reach me right now. And the time I have available right now, I'm trying to use to help others. So if you get a question or a concern that I might be able to help you with, contact me.
Yeah, and I'm sharing, Mark, I'm sharing that on LinkedIn, like his LinkedIn profile on the screen right now. So anyone who wants to, if you have any questions, any more
You can
questions?
put my LinkedIn profile on there.
Awesome. Yeah, I've already done that. Yeah, I can
Yeah.
everything, we can see it.
Not that I know of.
No, I would just say that we will finish on any final words from Billy.
Well, I've lived long enough to have a million stories, so I'd be happy to come back.
Awesome. I think we will connect we will talk to Wayne about it, and then he will connect, or I will connect with you for that. So I think we will be having you on soon again.
Well, best of luck to the EAT organization. I love what you're doing.